So I thought I'll be very much delayed, but then when I entered the door, it was like quite different from what I expected. I thought everyone would be waiting for me, but then it seems like I was not the one who delaying the things. Okay, great. I was in Gothenburg today, and I gave more or less the same presentation there this morning. So if there's anyone from Chalmers connecting online, so probably you can disconnect now. I'm from KTH. I was working with Infinera for 2 years, so there are many colleagues today. And Wolf is here, so nice to meet you again. Yeah, and then I joined back at KTH March last year. So because I got supported to do a project on this terrestrial wireless, and we have some progress that I would like to share with you today. So it's quite basic, nothing related to technology development yet, not like 100%. So this thing probably will be around 1 decade from now. So hopefully we will make it more attractive to the industry and to the operators. So yeah, these are the collaborators that I would like to acknowledge from Sweden, Denmark, China, Sweden again, and Spain and Latvia. So we have many collaborators to do this work. And a brief outline. First, I'll start with the history, like a story, beginning of the modern wireless communications. That's courtesy of Richard Sharps, who prepared this nice slides. I will directly use it. And then I would like to share a vision that we came up recently. And we hope we could use this vision to unlock certain limitations and create a more sustainable roadmap so that we can follow in both research and industrial development, not only for the next generation, but hopefully for a few generations ahead of time. Then I will move to a little bit more technical, the principles, how it works, and give a few examples of our recent experimental works. Then I will summarize and give a few remarks. Okay, I'll take a breath. Okay, so story time. The history. So, well, these are the textbook stuff, but it's always nice to look back. Hello, Jean. Nice to meet you. So, if we think about wireless communications, we automatically think about radio. So, at the dawn of the radio technologies, first we need some theoretical foundation. So, we know very well the Maxwell equation was reported or was presented in 1864 by the Scottish scientist James Maxwell. Then the very first radio wave demonstration was performed by Heinrich Hertz from Germany in 1887. Yeah, you might want to remember these years. And then the great scientist Marconi from Italy, who was also known as the father of wireless telegraphy, who developed the first tunable transceivers for radio transmission system. And then he demonstrated 1 kilometer telegraphic transmission in 1895. And 2 years afterwards, he extended the distance to 15 kilometers. And 4 years after that, he managed to transmit the radio signals over the Atlantic. And at the age of 35, exactly my age as of today, he received the Nobel Prize. So it was very inspiring. So these are the beginning of radio technology. It was like more than 100 years ago. Really, really impressive. Well, however, it's surprising maybe, the first wireless transmission in the modern history was not really made with radio. I didn't know about this until I learned from Richard a few years back. So it was the American scientist, inventor Alexander Bell and his assistant Charles Tanner in 1880. That was even a few years before the first radio wave demonstration. They already transmitted the first wireless telephone by using sunlight. The transmitter, they used a thin microphone membrane to modulate the voice onto the sunlight. And the receiver, at the time, there's no photodiode, no nice fancy receiver, so they use a crystalline cell. so to recover back this modulated signal, and then they could pick it up with the earphone. They managed to transmit already 230 meters in the DC at that time. So this was really, really impressive. According to Bell himself, he thought this was the greatest invention he has ever made, greater than the telephone. Yeah, probably he was the only one believing this at the time. So unfortunately, we see that after a few years, the telephone was all over the world, but this thing was never adopted because there were two fatal drawbacks. The first, it could only support line of sight transmission, so you need to see each other before you can transmit the signal. The second thing, it's really sensitive to weather conditions. So more than 100 years afterwards, as of today, these two factors are still the main drawbacks of free space optics. So we really haven't done anything fancier than this after 100 years. So let's see what we can do now. Well, as we have been observing for the past 4 decades, since the 2G wireless communication with microwave until now, the 5G, which is being deployed as of today, we need to, we are basically driven by higher and higher demand for data rate. And to do that, we need broader and broader bandwidth. And to do that, we need higher and higher carrier frequency to fundamentally resolve this limitation. And we started from microwave, and then now for 5G, we're already discussing millimeter wave. And if we look ahead, like 10 years from now, people are already discussing terahertz. So if we're talking about terahertz, it's basically sub-millimeter wave. And the upper bound of millimeter wave, 300 gigahertz, is corresponding to 1 millimeter wavelength in free space. And that's exactly the point. 300 gigahertz was the lower bound of far infrared, which is already optics from our definition or loose definition. So the properties of terahertz wave or even millimeter waves is already quite different from microwave because the free space loss it increases exponentially with frequency. So for millimeter wave and terahertz, we're no longer be able to broadcast everything like what we're doing with microwave. We have to do beam steering in order to have enough sufficient signal power at the receiver side to recover the high bit rate data that we would like to receive. So what we will encounter problems? First, we will encounter line of sight problem. So this has been one of the biggest problems for free space optics. So now we need to solve both. So, and another thing, if we're looking beyond 10 years from now, the bandwidth is still limited. We're a bit desperate. We're driven by the demand, and we are passively fulfilling this demand by increasing frequencies gradually. So what we can do? Well, what we think at this moment probably is a good idea, or probably it's not a good idea to exclude the possibility of using optics anymore. Because optics, as we know, bandwidth is the greatest advantage of optics. And since now we have both technologies, we have the same problems, we need to figure out how to solve both. So in our vision, we need to combine all the things that we have developed for both fiber optics and radio in terms of physical layer technology, modulation, coding, DSP, rotating beamforming. We have done a lot of works in both areas. So now it's time to merge them. And if we could, I have a mouse here, no, here. Yeah, if we could have a virtual layer standing between the applications and the physical layer technology and resources, probably we could figure out an intelligent way to synthesize the resources, regardless of whether it's radio or optics, and the media, either it's fiber, free space, and energy, with all the technologies that we have developed, accumulate over the years, and we select the best one to fulfill the requirements of the end user application. And then for the end user side, as long as the application services was supported with optimal performance, they don't need to know what are really exactly supporting them, either it's radio or optics. So this was like a very loose vision from our side. However, to do that, we will need the maturity or technological readiness level to be equal across the spectrum, which we're not which are far away from what we have today. So look at all these options from radio side, microwave, millimeter wave, which has been developed. I think the CMOS technologies today are very well prepared to support this development. So they are quite near-term vision for optics. We have ultraviolet, visible light, and the most mature solution is the infrared or near infrared, where we have the telecom band. So we have accumulated a lot of components, technologies from the fiber optics. We could reuse them. However, the most underexploited area is this. Okay, I don't see the mouse. Okay, here it is the terahertz band. So basically, from mid infrared down to the sub-millimeter wave, we haven't really looked much to use them. They have a broadband, we haven't really looked much to use them for communication purposes. And now we're talking about to use terahertz. So this is what we do at KTH, try to use photonics technologies to bridge this gap. So if we divide them into two parts, if we loosely put a boundary around 10 terahertz, so lower than 10 terahertz, they have closer properties to the radio signals that we have been using for wireless communications. And above 10 terahertz, they have properties closer to the optics, where we have a lot of experience with fiber optics, even though it's shifted into a longer wavelength. So I divide the discussions in two parts. First, the lower side of the terahertz band, where we use hybrid electro-optical approach to demonstrate a series of high-speed transmissions and assisted with photonics. And if we look at this graph, this is all these papers published in the past 1 decade, 10 years, starting from 2010. There are around like 80, 90 papers. And we see that with all electronic, there were already a lot of works with all electronic approach, with CMOS or 3.5 materials with HEMTs or HVTs. Up to 300 gigahertz, they work extremely well. They have very good power efficiency. They can made into very smaller size and footprint, and they can support already up to 100 gigabits per second. However, we do see, we do see there's a tendency of saturation because it's getting more and more difficult to make it work at higher frequencies. We have to fulfill all these signal integrity requirements, and it's getting more and more difficult to get high power and high tunability and higher bandwidth with electronics. Of course, there are still a lot of efforts put into this, but still, we do see the resistance becoming more and more pronounced. However, on the other hand, if we consider to include the possibility of using photonics to support the wireless transmissions in this frequency range, we don't see a clear sign of saturation yet. They have a very good match with the speed that we have already demonstrated with fiber optics. So up to over 200 gigabits per second has been demonstrated with a single spatial channel. So I will show you how we did it. So those dots on the top are all from our group and our collaborators. So this is a brief principle how it works. Well, it's quite straightforward. It's the basics principle of microphotonics, where you connect photonics with microwave by doing this photomixing. You have two light waves separated with a frequency difference and also have a phase difference. When you mix them at a photomixer, in this case a photodetector, we do the square law detection, and we will be able to generate RF signal together with a baseband signal. The RF signal will have a central frequency corresponding to the frequency difference between these two light waves. So, I mean, this principle has been widely used for different applications with microphotonics, and communication is just a small part of it. But for communication, this has a very good property, because if we do see that if we have a complex modulation here with both phase and amplitude modulated in one of the carrier, after this nonlinear square law detection, both the modulated components in in amplitude and phase are actually linearly preserved. There's no distortion at all. So all the modulated data are transparently shifted from the optics to the terahertz. So this is how we can generate seamlessly a broadband terahertz signal. And so this is the transmitter part. And the receiver, there are two ways, very similar to what we do in fiber optics. We have intensity modulation, direct detection, and we have coherent systems. So here's the same. If we have intensity modulated data or signal in the terahertz band, we could use an envelope detector to down convert everything to baseband. So we detect the envelope, we discard the high frequency part, we can directly have our data back. And if we have phase information included, then we can use this coherent detection. Yeah, the point is the same. Even though it's quite complicated, we could still preserve linearly the phase and amplitude modulation. So up to this point, we could have a from one end to the other end, up conversion, down conversion, transparent to the modulated data. So, and after this, whatever we have been using to process the digital coherent optical system, we can directly use it here. So all the experience that we have gained in fiber optics can be directly used to resolve these challenges. And based on this principle, we did a series of work. So the first work that we did in terahertz region was back in 2016, where we teamed up with DTU and Zhejiang University in China, and we made this single channel 100 gigabits per second transmission demonstration. We first, like any other fiber optic system, we need to modulate baseband data. What's different is that we generate a carrier that is stably locked to this channel, to the data channel, and then we do the photo mixing at a very high speed photo mixer. In this case, a unit traveling carrier photo detector or diode. This was a prototype made by NTT in Japan. I think they're still one of the best. They're still the best in making this kind of devices. And this has a frequency response up to terahertz, 1 terahertz, even over. And for 400 gigahertz, it has a very good response. And then we have a Schottky diode-based subharmonic mixer to down convert the signal to the receiver side. So we could use a series of digital signal processing to recover our data. And these are the constellations that we, after the DSP. So what we can see, I have a very clear clusters in all of them. And for 32 gigabyte, 16 corresponding to raw data rate 128 gigabits per second. And if we subtract the factor overhead, the net bit rate is already over 100 gigabits per second. And this curve down here, right, bottom side, these are the stability tests. And we run this system for over like an hour, something like that, and then the performance is really stable. And one more thing we did at the time is to, instead of using single channel, we use multiple channels, because the photo detector has really broad bandwidth. I mean, we are basically wasting its capacity if we're just using one single channel. And in this demonstration, we multiplied 6 channels together, each of 12.5 gigabyte. So altogether, the total growth rate is 300 gigabits per second, all emitted from this single terahertz emitter and pick up one by one at the receiver side. And for all these channels, because we have different response of the system, three out of 6 channels would reach below hard decision flag limit, and the other 3 reach below soft decision flag limit. And the overall aggregated bit rate was 260 gigabits per second. It has been a world record until last year, which we broke it ourselves. But the problem of this setup is, well, we're trying to make a compact transceiver to generate terahertz and receive it. But this setup occupies 2 big optical tables with a lot of amplifications, and you don't want to read the numbers that we consume in terms of watts of this big equipment. And also the transmission distance was quite limited. It's 0.5 meter, and we think we could do something better than this. So in the next few years, we gradually improved on top of this. The first thing we did was to use photonic integration. And we team up with a group in Spain where they have a very good experience in fabricating this dual laser. This one, oh great, we have a mouse. The dual laser chip in indium phosphide, and we could use a mode lock laser to generate a frequency comb, and we can lock these two lasers to have a very stable phase-locked tones out of this single chip. The chip is really tiny. It's like much smaller than this coin. I don't think you can see it clearly. But anyways, we have shrinked one of the table to a chip at least. But after this, we still need to use another optical table to do the modulation and everything. So in this work, we demonstrated 130 gigabits per second over 10-meter distance. So a lot of improvement has been seen with this method. The next step would be further integration, further integrating the modulators and the receivers, but this takes time. We're still working on it. And the second thing is the distance. So what we would like to explore the limit, and this time we did two things. The first, because this PD has a slightly higher power when we lower the frequency a little bit, so we lower the 400 GHz to 350, so we could have a bit higher power emitted from this photodiode, and then we also use quite big Cassegrain antennas to have a high gain, so that we could almost achieve lossless free space channel compared to what we did before. And with this setup, we could extend the reach of the system to the whole range of this lab, which has like over 25 meters of dimension. But we think we can go much further than this, but there are regulations that we cannot move these things outside. But as I said, this is also the first trial to extend the distance. We believe that we could go beyond a few hundred meters with the setup, because good question. I received exactly the same question this morning in Chalmers. No, it was quite painful to align with mirror. Any vibrations will give a quite big jump in the receiver performance. So we are quite limited with the signal-to-noise ratio at this speed. So well, if we could have some good or smart engineering solutions to align that, I think we could at least, as you said, double this distance with mirror indoor. But I mean, we have some progress to make it outdoor also. Okay, so this was already published last year. And one of the most recent work that we did was to explore the possibility of using spatial multiplexing. So in this work, we use both frequency and spatial multiplexing to finally demonstrate bitrate over aggregated bitrate over 500 gigabits per second. And this was the current record. And from what we feel, this was quite close to the channel limit. I think it would be quite challenging for anyone to beat it with the same method, unless they have some fundamental breakthroughs in their setup. So up to here is what we have demonstrated, and we have more works ongoing in the pipeline. It takes time, it takes effort, but this is just the starting point of this direction. So to give a brief summary, so to be frank, for applications 10 years from now, we don't need this. We believe CMOS technologies up to 300 GHz will cover everything, because it's already quite mature. We do see that the 100 gigabits per second has been demonstrated, and if we compare the power consumption and potential cost and size, yeah, I mean, CMOS wins in all aspects. However, we do see there is a limitation of this CMOS technologies to go beyond 300 GHz if we need one order of magnitude higher bandwidth. Then we are running into a limit. So even for now, if we're talking about high-end applications where we would like to have a quick installation and have a much faster than 100 gigabits per second wireless or free space channel, this photonics-assisted approach can be considered because it has a seamless integration possibility with fiber optics, and it is also much higher bit rate, which also keep closely up to the state of the art of fiber optics. So we hope it may play an important role in certain use cases when we need higher frequency, broader bandwidth for the future ICT infrastructure. And hopefully we could make it really work to the industrial standard 1 to 3 decades from now. So 3 decades from now, I won't care much because I will retire, but hopefully this will keep myself busy for the next 30 years. And yeah, thanks a lot.
So now we have some time for a few questions. For, you know.
Yeah, please.
Now I'm just curious, I mean, vision now, when you see those little names, driving towards the norm.
Yeah, good.
I mean, in 10 years' time, to drive this.
Yes, I have been trying to make up one until recently read the news, this metaverse. You see that you don't want to be stuck in a scenario where the physical layer is the bottleneck, right? So we need to be well prepared for this three-dimensional. If you consider, if we're talking about 8K video signal now, it's already above 50 gigabits per second requirement. If we consider in 3D, this is basically another order of magnitude higher demand. So if we're talking about the metaverse, really, then in real time, if we don't compress the signal, everything, we need much higher data rate. So this is a good argument. I didn't really think of myself, but when I read the news, okay, I have a good motivation. No. Yeah.
You only trusted the digital signal, so not like analog.
No, yeah. So yeah, analog signal. Yeah, analog signal itself has some. I think we have background in fiber optic communications, and it has been a tendency that we stick to digital transmissions over the past 10, 15 years. So analog signal, we have studied for some time analog radio fiber signal, but then we believe that it's much easy and to regulate. We put everything digital.
Yeah, I just wonder if you have any comments on
yeah.
If you think about the analog your fiber, but you not
yeah, with digital transmission, we still have nonlinear distortions from modulation, from transmission, and also from this up and down conversion. Even though theoretically it's linear, but when we pump really a lot of power into these devices, we run into nonlinear region. And the system has memory, so whenever there's memory, we have nonlinear beatings everywhere. So it's a big problem. But I think a digital system has a bit higher tolerance in terms of nonlinearity compared to analog.
Could you just probably comment about the amplification of the campus?
Right. Amplification, yeah, it's quite challenging to do amplification above 400 GHz. There are low noise amplifiers already developed, but all with this 3.5 material. Above that, we don't really see any broadband amplifiers available, and there are a lot of work, a lot of effort put into these areas, but we do hope that we will have something. We're not the only one who work on this, so there will be parallel efforts from all the other groups worldwide to work on different things. Amplification is one of the most important.
And you always needed
No, we don't have much amplification here. No, because we don't have amplification possibilities material restriction. Yeah, because the gain of the antenna, so we try to really narrow down the beams into more or less lossless scenario. If you see the effective aperture of these antennas up to a few tens of meters, is actually lossless because the gain of antennas combined is larger than free space loss. You calculate.
Maybe one can say also that quantum cascade for higher frequencies, then quantum cascade amplifiers are developed now.
Yeah, I skipped that second half of the time. We also work on quantum cascade. Henrik, you're too polite.
No, I was actually wondering about that. Is that mature technology or is that something that's probably?
It's not so mature, but that's the easiest part so far. It's passive. It's passive devices. It's engineering.
Yeah.
You find proper coating. Now I think it's gold, and, or you can use lenses, polymer lenses. That's good. Coupling, very low insertion loss, and very good gain. So, but I mean, the challenge is to make them smaller and make them actively tracking the beams. Those are quite difficult to handle. But those are things that will keep us busy. Okay.
Then can you still work about why using the terahertz compared to visible light or other wavelengths in free space? What's the advantage that the frequency you already level?
I mean, the visible light is very good for indoor communications. But visible light is basically a compromise because it's not laser, it's not coherent. It's a compromise for the illumination function. The illumination is still the highest priority for visible light communications. So the coherence of these LEDs not very good. So the bandwidth of these LEDs are also very small. They have different application scenarios, but for visible light communication, we don't really think high speed is one of the most attractive feature of it. But as I said, all these segments or frequency windows in the electromagnetic spectrum from the radio to the optics are equally important. So we need to develop all of them. Hopefully we could have equal maturity of all these technologies across all the spectrum 20, 30 years from now, so that we can. So we are the ones who decide which one we pick, not the technologies we decide.
Okay, thanks very much.
Thank you very much.
So now we will serve up food.